Hi guys, good morning. Hope everybody's there. Only three of you are there. Shall we wait for 2 more minutes? Let your friends join. Guys?
Okay, sir.
Yeah. So how's it going, people? Other subjects? Hmm? Are you finding it easy?
Yes, sir.
Can you text your friends if you have their numbers? So please join soon. Please, do you have their numbers? Anybody's number?
Sir, I don't know anyone.
So,
Okay.
say one has a power cut in his area, sir. So, it's not.
Okay. 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 Total is almost 7 people, right? 7 or 6 people. Not even 50%. Any exams are going on in your school?
For me, it's completed, sir. I don't know for others.
Okay.
So for me, it's next week.
Next to next week. Okay. Hey, guys, I'll just call Akila and see what I can do. So I'll be back in 1 minute. Okay.
Last one more. Okay. Aditi, can you text your friends if you have anybody's numbers? Please ask them to join soon. Text or call. I'm not able to speak. I don't see any speaking option. Ritik, are you able to hear?
Yes, sir.
Nice. Hello?
Yes, sir.
No, I'm not able to hear you. Join. Just go back and join again. 1 second.
Okay. Yes, can you speak something? Let me see.
Yes, sir.
Yeah, cool. Good to hear. Fine. So I think we have three. We'll start with whatever we have. Right. So if you can remember, people, right, we were talking about isomerism, right? So we said that isomerism is a phenomenon where molecules have same molecular formula but different structures, or they can have different orientations of atoms in 3D space, right? So based on that, we went on to classify isomers into two types, that is structural isomers and stereoisomers, right? So under structural isomers, I had chain, position, functional, metamerism, ring chain, tautomerism, all these things we have. And when I go for stereoisomerism, I had only two, right? That is optical isomerism and geometrical isomerism, right? And then we saw few examples. We saw a little bit about the structural isomers, right? I told you what is chain, position, functional. We know, right? Functional is like same molecular formula, but different functional groups, right? So that and all we saw, right? So today we'll concentrate on what is metamerism and tautomerism, right? Okay, so we'll start. Right. So metamerism, right? So metamerism is not seen in every compound, right? So there are going to be certain specific compounds. Only in those compounds I'll be seeing metamerism, right? So you can argue with me, say, like if I teach you what is metamerism, you can argue with me saying that sir, this is nothing but chain isomerism, but it is not. It is not exactly like that, right? Okay. Uh, Please understand, for metamerism to happen, right? For metamerism to happen, I know generally what happens in a straight chain compound, right? In a straight chain compound, all the atoms are going to be carbon atoms, isn't it? Because in the straight chain, all the atoms are going to be carbon atoms, right? But if there are compounds where in the straight chain, say one of the carbon atom is replaced with some other element. Say for example, in case of your ethers, what happens there? In between two carbon atoms, I have an oxygen atom, right? Same goes with your secondary or tertiary amines. Again, one of the carbon atom is not there. There I have nitrogen, right? So in these kind of cases, where in between two carbon atoms I have an element, right? So only in those cases metamerism is possible. Okay. Say for example, how will we take examples? Let me give it like this. For example, if you have say C4H10O, okay, I have C4H10O, right? So I know I can write alcohols for this, right? I can write chain isomers, position isomers, and all these things I can write. Obviously, I can write ethers also, right? Because you can see CnH2n plus 2, no unsaturations, right? So there are only two possible functional isomers. One is alcohol, the other one is ethers, right? Okay, so when I concentrate on ethers, right, say what are the structure of ethers I can write? So one possibility can be CH3, CH2O, CH2, CH3, right? This is one of the possibilities, right? Now what you see, in between two carbon atoms, I have an oxygen atom. That is not an issue. But what you see is in both sides of the oxygen, I have two carbon atoms. Correct. Now instead of writing it like this, I can write it like this. Say I can write it as CH3O, CH2, CH2, CH3. Yes, right. So again, what do you see? So these two basically are what are called as your metamers, right? These two, you see two carbon atoms on either side. Here I have one carbon atom and three carbon atoms on either side, right? So these two are what are called as metamers, right? So I can even write one more structure, one more metamer I can write. Say I can even write it as CH3, CH, this one, right? Again, this is also going to be a metamer of these two, right? So guys, did you understand what I'm telling? Right? What do you mean by metamers? For metamerism to happen, right? In between two carbon atoms, I should have some other element, and I should have difference in the chain length in both sides, right? Between the two metamers, right? Again, this can even happen with nitrogen, obviously, right? So if I put this in place of oxygen, if I put NH, that is a secondary amine, again I can have these kind of structures coming. Is it not? So these are what are called as metamers, right? So guys, everybody understood what are metamers? Please give me yes.
Yes, sir.
Okay, right. So that is about metamers. It's pretty easy, right? Now we'll move on to automerism. Okay. Now this is a special type of structural isomerism, right? So why do you okay? Anybody knows what is automerism? Hmm? Anybody wants to give me at least a gist or whatever you know? You want to tell me?
No idea, sir.
No idea. Okay, fine. So please understand, people, this is the only type of isomerism, right? Among all the isomers, right? This is the only type of isomerism which is actually happening in reality. In the sense, right? Say if I give you a molecular formula like C4H10O or whatever it is, right? You will be able to write structures on the paper or say on the board. I will be able to write so many structures. But does that mean that if I have one of the isomer, the other isomer will also exist along with that? Did you understand my question? What I'm telling is, say I give you a molecular formula, right? So you can write so many structures for that molecular formula. Agreed, right? But the question is, say, okay, let me write like this. I have right. So if I have these two compounds, they have same molecular formula but different structures, right? So now both of them will have a molecular formula of C4H10O, correct? Right. So the question is, if I have this particular compound in a test tube, right? Is there any possibility that this compound can also exist in the same test tube? Hmm?
So, uh, what are you trying to say, sir?
What I'm trying to say is, say I have these two are isomers, same molecular formula, right? So what I'm asking is, I have a test tube in which I contain one of them, right? So I have this one, right? So what I'm asking is there any possibility that this compound can also be there along with that test tube? That means I'm asking, will this molecule change itself to this compound? Is what I'm asking. Is there any possibility? Yes? No? Okay. Just give me an yes or no. It's a blind guess.
No, sir.
Okay. So obviously, right, how will I have, right, I have taken only one, I have taken a test tube which contains only any one of the compound. There is no possibility that the other compound will also exist in that particular solution. Impossible. That or in other words, I would say that this compound cannot convert itself into this compound, or say this compound cannot convert itself into this compound, right? But in case of tautomers, right, that's exactly what is going to happen, right? So basically, tautomers are a special type of functional isomers, right, which are capable of interconverting themselves, right, which are capable of interconverting themselves. That means if I have a test tube containing one of the tautomers, right, there is a good possibility that the isomer of that, that is the tautomer of that, can also exist in that particular test tube because they will be able to undergo interconversion, right? So that special thing is what is called as your tautomers, right? So there are so many types of tautomerism, but in our syllabus we have only this, that is called keto enol tautomerism, right? So we have keto enol tautomerism, right? So what is this? Let's see. So from the name itself, you'll be able to guess what exactly is happening, right? So I have a ketone or an aldehyde, right, is going to get converted to an enol. Enol is C double bond C with an alcohol, right? So they will be able to undergo this interconversion. If one of the compound is right, okay, if I have a ketone, that ketone can convert itself into an enol form, or say enol form can convert itself into an keto form, right? So this is what is called as tautomerism. So we'll see how it happens, right? Okay. So let me take any ketone for that example. Say I have CH3CO CH. Okay, right. So I have this ketone, right? Now before we go on to answer this, like see what exactly is happening. Now please tell me, everybody knows what is the mechanism for aldol condensation? It should have been over in your school, right? Very important reaction for in your board exams point of view. Yes, everybody knows aldol condensation. No, it has not been taught yet. Guys, we already have less number of
It
people.
has been, sir.
Okay. So it has been taught. Okay. So please tell me, what is the first step in aldol condensation? What is the first step in the mechanism? So I assume that.
Right.
Ah,
I don't
yeah.
remember, sir.
Okay. What about others? What is the first step in aldol condensation? Akshay, Siddharth, any idea?
So it will react with the base. So
Okay. It will react with the base. Correct. What will happen?
and then it will form an aldehyde.
Okay.
It will form an aldehyde or a ketone.
Mm, okay, fine. So that means maybe they didn't teach you the mechanism properly, or you don't remember. Right? Either of the two choices. Right. Okay. So please understand, people. Right. The very reason why aldol condensation reaction occurs. Right. Why is it happening? Right. The main reason behind it is because I have this acidic alpha hydrogen. Very, very important, right? So why aldol condensation reaction occurs is because all aldehydes and ketones will have acidic alpha hydrogen, right? So we know what is alpha position. So this is the main carbon atom, right? The C double bond with the carbonyl carbon is what is my main carbon atom, right? So this is my alpha carbon atom. This is also my alpha carbon atom. Obviously, if I have one more carbon atom after that, it will become beta, right? So what I'm telling is, in all aldehydes and ketones, right, I'm going to have alpha hydrogens to be acidic. What are alpha hydrogen? The hydrogen atoms in the alpha carbon atom is what is my alpha hydrogen, right? So these alpha hydrogens can come out as H plus, is what I'm trying to say. When I say alpha hydrogens are acidic, that means this hydrogens can come out as H plus. Okay. Now, please understand, people. We'll be speaking about this acidic strengths, basic strengths, more and more in the due course of this. In this chapter only, we'll be speaking. In the general organic chemistry, we'll be speaking. But for now, please understand that when can something act as an acid? Is the question, right? So the thing is, hope you know what is called as conjugate base. Any idea what is conjugate base? Conjugate base of an acid. Do you know what is that?
It's the base it reacts with.
No, not that. Right. See, okay, let me tell you that first. Right. Say for example, I have HCl. Okay, HCl is an acid. Right. So please remember that after removing H plus from the acid, after removing H plus, whatever is remaining is what is called as your conjugate base. For example, in this case, after removing H plus, what is remaining? Cl minus. So this Cl minus is what is called as my conjugate base of HCl. Okay, right? So after removing H plus, whatever is remaining is what is called as my conjugate base. Okay, so in this case, Cl minus is my conjugate base, right? So why we started this is because in organic chemistry, how do we decide whether particular substance can act as an acid is based on this conjugate base. Okay, so if you find that the conjugate base is stable, right? If you find, again I repeat, if you find that the conjugate base is stable, that means that particular substance can act as a good acid. Again I repeat, if you find that the conjugate base is stable, right? Again, how do you determine whether stable or not? That will come later, right? So first thing is, if you find that the conjugate base is stable, that particular compound can act as an acid, right? So that's the point, right? So keeping that in mind, right? Keeping that in mind, so I'm telling from this alpha positions, I will be able to remove an H plus, right? So we'll see what happens, right? After removing H plus, if I find that the conjugate base is stable, I can say that yes, this particular compound can give me H plus. It's a good acid, is what I can say, right? Let me see what is happening. So from this, if I remove H plus minus H plus, again, please understand, I'm not removing H plus from any random position. I have to remove it only from the alpha position, right? I have to remove it only from the alpha position. Only alpha hydrogen is acidic. Say if I have one more carbon atom which is having CH3, from there you cannot remove. Again, why? Because at that position, if you remove, the conjugate base is not stable. That's why. But we'll prove that here it is stable after removing H plus. So you will see, say if I remove this one, say I will have CH2 minus after removing H plus, C double bond O, CH3. No issues, right? Now, with all the knowledge you have from organic, guys, tell me how this is stable. This particular anion, how is it stable?
Resonance, sir.
Good, good, right? So I can easily see that this particular thing can come here and the carbon oxygen bond can break, right? So now how will I write the structure for this? I have CH2 double bond CO minus, right? And CH3. No issues, right? So basically, all these, this is the first step which happens in your aldol condensation, and this is the same reason why tautomerism is also possible, right? So if someone asks, we didn't complete it yet, we have completed, but wait. So what I'm telling is, if someone asks you, what is the reason behind ketones and aldehydes showing tautomerism? The answer is because they have acidic alpha hydrogens. Right. Okay. So till now, any doubts? Till now, I think everybody understood. I just removed a H plus. I wrote the resonance structure here. I just put this bond here, and I just put the negative charge as a bond here, and then I broke my carbon oxygen bond. Right. Okay. Now, please understand. This is not complete yet. Right. Now, why is it not complete? Is because the molecular formulas are not matching. Now, if you look at here, I have something, but here there is one hydrogen atom missing because I have removed a hydrogen atom, hydrogen plus, right? So that has to be added. So where will I add it? Tell me. In this case, in this molecule, tell me where will I add the hydrogen?
With the oxygen, sir.
Good, right? Because I have a negative charge. So obviously you remove the H plus, add the H plus. So CH2 double bond COH. Right? So people, this and this are what are called as your tautomers. Keto form, enol form. Enol. Is it not? I have a double bond with an alcohol. Right? So this is what is called as keto enol tautomerism. Right? So very easy, right? What you have to do? You have to remove the H plus, right? Make the negative charge, make the resonance structure, add the H plus along with oxygen. So the initial structure and the final structure you're going to get are what are called as tautomers. And this happens in reality, right? Say if I have a test tube full of acetone, this is my acetone, right? So it will not be 100% acetone. Say it might be 98% acetone and 2% of this form. So this happens in reality. That's why we don't study them under functional isomerism, because it doesn't happen in reality. You can write so many structures you want, as many as you want in papers, right? But it will not happen in reality. But here, this is a very special case which is happening in reality, right? Okay, we'll take one more example like this. So guys, everybody understood what is tautomerism?
Yes, sir.
Yes, sir.
Okay, cool. So we'll take more examples. Right. Say I have I have this particular compound. Right, this is my ketone again. Right. So now if I'm asking you, write the enol form of this. Right. Can you try? Just try. Anyways, I will do. I'll give you 1 minute. Take a pen and paper and draw the enol form. Draw the structure of enol of this. Go for it. See, organic chemistry, you cannot sit without a pen and a paper. Right? There'll be a lot of times I'll be asking you draw the structure, write the mechanism, what happens here, all these things I'll be asking. Right? Do exact same thing what we did last time. Remove the H plus, make the negative charge, draw the resonance structure, add hydrogen to the oxygen. Simple. When you're done, tell me you're done.
Sir, I missed it.
Okay, fine. We'll check what the. I can just check when I'm writing the structure whether you were correct or not. What about Siddharth and Akshay?
Got it, sir.
Oh, fine. So we'll see. So now you have two possibilities of getting an alpha hydrogen. Say, please understand, this is one alpha position, this is another alpha position. There is no restriction, right? So actually, if I have two different groups, that will be too much of technicality. You have to choose whichever is more stable. But again, we will not go into those things. For now, it is equivalently. You can take it from anywhere. Right. So let me take it from here. So removing H plus minus H plus from the alpha position from here, if I take, say, I would have had a negative charge here, a double bond O, no problem. Now I have to make the resonance structure. Now this will come here, this will break, right? So now next thing would be, I have a double bond here, yes, and I have a O minus. Now you remove the H plus, add a H plus. So one double bond and O. So did you get the structure?
Yes, sir.
Yes, sir.
Yes, sir,
Aditi?
but I did it on the other side.
No problem. Same thing, right? Okay, so again, these two are what are going to be my tautomers, right? Keto form, enol form, right? One more example. Yes. When you try this, you are going to get a very familiar compound. And you have a doubt, right? Sir, I have two positions. One is here, one is here, right? Please understand, you cannot remove H plus, not only from here, right? Unless and until if it is going to be an alkyne, I'll tell you when we go for acidic strengths, you cannot remove a H plus generally from sp2 or sp hybridized carbon atom. Okay, this is sp2 hybridized carbon atom. You cannot remove H plus from that, right? So the only possibility I have is I have to remove H plus only from here, right?
Sir,
Ah,
is it phenol?
yes, absolutely true, right? So if you write the enol form, basically I'm going to get phenol, isn't it? Right? So again, a simple thing. So I removed H plus. Let me make a negative charge. This will come here. This will break. So I would have had already a double bond here, double bond here, double bond here, and a O minus. If I put the H plus, it is going to become OH. So yeah, this is key. Okay, right. So yeah, this is about tautomerism. Okay, so keto, enol, tautomerism. Right. So there are other compounds which can give tautomerism, but it's not important for you. No question is gonna come. Question if that comes, it will come from this only, right? Okay. So what other? But anyways, I can give you one or two examples of in which other compound tautomerism is possible. So it is possible with cyanides, right? So cyanides, say for example, I have CH3, CH2, CN, cyanide, nitrile, or whatever it is, right? So this particular hydrogen or this particular alpha hydrogen is also acidic, right? So same thing can happen what you have with your ketones. Okay, say same thing, right? So I can, if I remove the H plus, it is going to become CH minus, right? I have C triple bond N, right? So now what is going to happen? This will come here. One of the triple bond would break, right? So I would have had CH3, CH double bond, C double bond N minus, isn't it? This bond came and I have broken the pi bond, so nitrogen will have a negative charge, right? So I have this thing. So obviously I have removed a hydrogen, add a hydrogen, so I can just remove this and put a H, right? So these kind of compounds, whenever you have a C double bond NH, right? So these kind of compounds are what are called as your imines, IMINES, imines,
Sir,
right? So your yeah.
there won't be a CH2, sir, instead of CH.
There won't be a CH2 instead of CH. No, I removed a H plus, right? Here. I had a CH2. From
Oh,
here,
two
I
or
removed
I
a H
thought
plus.
three, sir. I thought
Oh,
that
yeah,
three.
this is 2. Yeah, it's 2. Right? So, yeah. So, this is what is called as your imines. So, your cyanides and imines are tautomers. Okay? Even nitro group is capable of doing this, NO2. Right? NO2, again, if I have an NO2 here, right? So even that is again acidic. I mean, I have acidic alpha hydrogens. Okay, so even that can form tautomers, right? But again, 90%, 95% you'll not be getting questions from that. Right? If at all you get questions from tautomerism, it will generally be from ketoenol tautomerism only. But if not, I'll just tell you what are they: ketones, cyanides, and nitro compounds, NO2 group. Right? Okay. Now tell me whether uh, yeah. Now tell me, can this compound show tautomerism? I have, what is it? Not acetophenone. Acetophenone, right? Now tell me whether this compound can show tautomerism.
No, sir.
Why?
Sir,
Oh,
because
see. Wait. Okay, this is also a pH. Now tell me. Yeah, why?
the carbon atoms are sp2 and sp hybridized, so we can remove H plus.
Okay, that is one reason. Another reason? If you look at this properly,
Sir, there is no alpha hydrogen, sir.
that's the answer which I was expecting. Right. There is no alpha hydrogen for me to first of all remove. Correct. So whenever you see there is no alpha hydrogen, tautomerism is not possible. Please keep this in mind. Okay. So the only condition which is required for ketones to show or aldehydes to show tautomerism is that I need to have at least one alpha hydrogen. If there is no alpha hydrogen, no tautomerism. Okay. Right. Cool. So yeah, that's about tautomerism, people. Right. So we have completed all your structural isomerisms. Okay, right? So question like structural isomerism is relatively easier when compared to stereoisomerism. Right. Okay, cool. So yeah, that's about tautomerism. Now we'll move on. We'll move on to stereoisomerism. Right. In stereoisomerism, we'll start with geometrical isomerism. Okay. So geometrical marker. Right. So geometrical isomerism. Okay. So we already know some gist of what geometrical isomerism is. We know the cis and trans is what we are going to study, right? Okay, fine. So the thing is, right, when I have a C double bond C, right, when I have a C double bond C, okay. Now please understand, this C double bond C will not be able to rotate, okay. But if it is a single bond, C single bond C, right? Now this particular bond can rotate. Now, how do you visualize this rotation? I'll tell you, right? Now, please look at this. I have basically an electron pair shared here, right? One is having a clockwise spin, the other one is having an anti-clockwise spin. Okay. So how do you have to visualize this rotation? Is like this. Say this is how they're going to rotate. Say one in clockwise, other in anti-clockwise. I mean, I'm not able to make you make the rotations properly here, but I hope you understand. It's like this, like twisting, right? So that kind of rotation is what we see in C single bond Cs. And because of the rotation, again, I have a different, entire different type of isomerism itself, right? So those are what are called as conformational isomerism. We'll see that later. Okay, but this kind of thing is not possible when I have C double bonds, because what do you see, if I'm going to rotate it like this, right, so obviously the bond will break. I mean, what bond will break? The pi bond will break, right? So C double bonds will not be able to undergo rotations, right? So that is why we are even seeing it in the isomerism, right? Because if it is going to rotate, right, obviously I'm going to have different orientations of atoms in space because of the rotation, right? If it is going to happen because of the rotation, I have some other name for that. That I told you, it is called conformational isomerism, right? But here, if it is like, it's not going to rotate, but we can change the orientations in the paper. That's what we're going to see, right? We are going to change the orientations of atoms in the paper. We are going to put some different positions here, right? Now, for so generally only alkenes will show this geometrical isomerism C double bond Cs, right? Now there are going to be certain conditions which has to be satisfied for an alkene to show geometrical isomerism. Okay, there are going to be certain conditions which have to be satisfied for it to show geometrical isomerism, right? So what are the conditions? Is first condition is obviously I should have a C double bond C, right? I should have a C double bond C, and this C double bond C should be like this only, right? So you have two carbon atoms involving in this double bond, right? So both these carbon atoms, I'm going to have two groups attached to them, right? Now these two groups attached to each of these carbon atoms should be different, as simple as that, right? The two groups attached here and two group, not, I mean, see, I'm not even connecting these two. I'm not even connecting it. There's no connection between these two. I'm telling about these two, right? Now these two groups must be different. Say if at all it is A, this should be B. I cannot have A and A, right? Same way, if at all if this is A, this should be some other group. Or I can even have entirely 4 different groups also, no problem. I can have A, B, C, D, right? But the thing is, these two groups, that is this and this, should be different, and this should be different. Is what very important, right? Okay, so obviously we know what is this, what is trans. In this case, whatever I wrote is
Cis.
this, right? You can see A and A are on the same side, B and B are on the same side. So this is my cis, right? And obviously trans will look like this, A here, and opposite side is A, B and B will be opposite. This is my trans, right? Okay, so this is very easy, right? Okay, so generally we say trans is more stable, right? Why generally we say trans is more stable? We generally say that trans is more stable. Why?
Sir, it's distributed.
Okay, it's distributed in such a way that
More balanced.
So it's all about repulsions. Okay. So in trans, I have less repulsions between the groups, right? But in cis, since they are on the same side, right? So obviously, I'm going to have higher repulsions there, right? So the reason why trans is more stable is because they have lesser repulsion when compared to cis. That's the reason why they are, more stable. Okay. Now, you can call them cis and trans if you have an arrangement like this, say AB arrangement. If you have, you can call them like basically you can call them as cis and trans. But what if all the four groups are different, right? So at that time, you will not be able to call them as cis and trans. You have some other naming like methodology for them. So we'll see what is that, right? Right. So whenever you have C double bond C, A, B, C, and D, right? You cannot call them as cis and trans. There's another kind of isomerism called as EZ isomerism. Exactly similar to cis and trans, but there are certain extra things which you have to do whether to decide whether it is going to be E or Z. Right now, please understand E corresponds to trans and Z corresponds to cis. Okay, let me tell you how are you going to do it. But for now, please understand that E corresponds to trans and Z corresponds to cis. Okay, fine. Now it's very simple. How are you going to give these notations E or Z, right? So what you are going to do is that for these two groups, say for each of the carbon atom, involved in the involved in the double bond, right? You are going to assign priorities, right? So basically, you are going to assign 1, 2 for this side. Same way, if you're going to do 1, 2 for this side, I'm going to assign priorities, right? So what you see here, I'm just putting random things, right, for you to just understand. So you can see 1 and 1 are on same side, 2 and 2 are on same sides, right? So now that will correspond to cis generally. So we cannot call it as cis. So I'm going to call this particular thing as Z isomer. Okay. And if we find 1 and 1 here and 2 and 2 here, then that is going to be called as E isomer. Okay. So the next natural question which comes to you, right, is, sir, how am I going to assign priorities? Based on what? Very simple. Priorities are going to be based on more priority. I mean, like it's going to be based on atomic numbers or molecular masses. Atomic numbers or atomic masses, right? So it is going to be based on the atomic masses of that particular group involved there. Okay, we'll take an example, right? Say I have C double bond C, F, H, Cl, Br. Okay, all four different groups, right? Okay. Now, see, again, there is no connection between these two. You have to go, you're going to assign 1 and 2 for this two, 1 and 2 for this two, right? And whichever out of these two, whichever is going to have more atomic mass will have more priority, right? So obviously, if I do for these two, among chlorine and bromine, which is having more atomic mass? Among chlorine, bromine, which is having more atomic mass?
Bromine.
Bromine, right? Obviously, it comes fluorine, bromine. Bromine will definitely have more atomic mass. So priority 1 goes to bromine. Obviously, second priority goes to chlorine. Done. Right. Now, these two, tell me which is having first priority, F or H?
Fluorine.
Right. So fluorine has first priority, hydrogen has second priority. Now, what do you see here? 1 and 1 are on opposite side. 2 and 2 are on opposite side. So definitely this is going to be my E isomer. Right. Say one more example. or which? Okay, can you do it and tell me whether it's E or Z? This is C2H5 ethyl group.
Z isomer.
Sorry,
Z isomer.
Z isomer. Okay, we'll check. Right. So fine. First, these two, first priority obviously goes to this. Second priority goes to this because obviously this is bulky. This atomic number only one or atomic mass only one. Right. So among iodine and OH, definitely iodine has more mass. So one, two. So obviously you see one and one on same side, two and two on same side. So definitely this is going to be Z isomer. Okay. So hope everybody understood what is E and Z and how do you assign E and Z for the molecules. Okay. Right. So yeah, that's about geometrical isomers. But again, I can make it relatively tougher if you have more than one double bond. Right. So if you have more than one double bond, you have to slowly do it. Okay. So let me take an example. Right. Right. Say for example, if I have okay, let me have this kind of structures. Okay, I have two double bonds here. Right. Now, how will you go about it? Tell me. Can you think and tell me how many isomers, how many geometrical isomers are possible for this particular molecule? You think, but there is an easier way of doing this. So first thing what we look at is this molecule is symmetrical, isn't it? Right? This molecule is symmetrical. Correct. Right. So if you have symmetrical, it is going to become a little more easier. Okay. Now, very simple, right? You don't even have to draw the structures. You can just think like this. How will you think? Say, I'll call the first double bond, like say one of the double bond can be cis. Say the first double bond is cis. The second double bond can also be cis. What is the other possibility? One can be cis. The other can be trans. Or what is the third possibility? Both of them can be trans. Right? So that's it, right? These three are the only possibilities. So I have three isomers for this particular molecule. Everybody understood what I'm trying to say?
Yes, sir.
Yes, sir.
So if the molecule was not symmetrical, for example, if I had CH2, CH3, then how many would have come? Tell me.
One, sir.
Totally only one. Or just think, if you can understand the previous one, what other will come extra? Obviously, these three things are already possible, no doubt. Other than that, what is one more possibility?
Trans is, sir.
Exactly right. So since it is symmetrical, I mean, the last time it was symmetrical, I put cis trans or transes will make only one because that is symmetrical. But in this case, cis trans, this can be cis, that can be trans is one thing. definitely that being cis and this being trans will make a different molecule because it is not symmetrical, right? So in this case, you will not get 3, you will get 4. Why? Because along with cis and trans, you have trans and cis also, because this molecule is not symmetrical. Did you understand? Right? So very simple, right? So if the molecule is symmetrical, very simple, just go for the combinations of cis and trans, right? If the molecule is not symmetrical, then think, right? Obviously, if I have cis and trans, if I put trans and cis, definitely that is going to vary because this molecule is not symmetrical. Okay, right? So we'll do a couple of problems on geometry isomerism. Right. Okay, right on the question. How many alkene isomers? How many alkene isomers are possible? How many alkene isomers are possible for C5H10? How many alkene isomers are possible for C5H10? So they're asking you only alkenes because obviously for C5H10 I can even draw ring structures. That you should not go, right? They're telling only alkene isomers. How many such alkene isomers are possible, right? And see, they didn't specify anything about whether it's structural or geometrical, nothing. So everything has to be included. Okay, tell me the answer. How many? C5H10. Yes? Any answers? Any numbers? Guys, please don't sit without trying, right? It will be boring for you. It will be boring for me also. Yes. How many?
Sir, I did 3, sir.
3. Okay. We'll see. 3. I have options like 3, 4, 5, 6 on the options. So you
But
are
four.
going. You got 4. Okay. Who was it Akshay? Or Siddharth?
Yeah, sir.
Okay. Fine. So we'll check what are the possibilities. Okay, so it's C5H10. So let me draw the normal structure, straight chain, without any branch. Say I can put the double bond in the first 2 carbon atom itself. This is 1, right? Can it show geometrical isomerism? Can this molecule show geometrical isomerism?
No, sir.
Why? Why it cannot show geometrical isomerism? What is the condition I told you for geometrical isomerism to be shown? Just now we saw, right? What is the condition?
So the two groups should be different.
Exactly. So what is happening here? You see, there are 2 hydrogen atom attached to the same carbon atom, right? So this molecule cannot show geometrical isomerism. So there is only 1. So everybody understood why this cannot show, because you see there are 2 hydrogen atoms which are similar groups, A and A. It is not A and B, right? So this cannot show geometrical isomerism. Okay, fine. So in this itself, let me make some branches. Say I have CH2, CH. Now I can put 1, 2, 3, 4, 5. Okay, done. This is another possibility. These are chain isomers. Okay, so this is one more possibility. Now, any other possibility with the double bond in the first position? I don't think so. Right. Okay. So next, I'll just shift the double bond to the next position, that is between 2 and 3. So I have CH3, CH, double bond CH, CH2, CH3. Right. Okay. Now, can this show geometrical isomerism?
Yes, sir.
Yes. How? Because I have, so this carbon atom, if you check, I have a hydrogen, I have a CH3, 2 different groups. Again, for this hydrogen, C2H3, different groups, right? So definitely this can show geometrical isomers, or obviously it will show 2 isomers, cis and trans. So for this itself, I have 2. Okay, for this itself, I have 2. Okay, next. Again, I can make branches. Can I not? Yeah, I can. CH3, C, CH3, double bond, CH, CH3. Another possibility. Can this show geometrical isomerism? Can this molecule show geometrical isomerism?
So
No,
no.
sir.
No, sir.
No, obviously, right? Because why? I have two CH3s, same group. Both the carbon atoms should have two different groups attached. If not, no isomerism. I mean, no geometrical isomerism, right? So again, this case, no geometrical isomerism. Okay. Any other possibility can we have? Double bond between, again, if you put it in between these two carbon atoms, again becomes 2 and 3. So yeah, these are the possibilities. So let me count how many. 1, 2, 3, 4, because there are 2 and 5. Totally 5 geometrical, 5 isomers. Any doubts, guys? Everybody understood how is it 5?
Yes, sir.
Okay, so this cannot show geometrical isomerism. This also cannot because there are 2 hydrogens. Again, this also cannot show because there are 2 methyl groups in the same carbon atom. So only this can show geometrical isomerism, right? Okay, cool. Now let me ask you this question. Let me see if you can answer.
So can you explain again how we get 5 isomers?
So the structures, no problem.
No problem.
Structures, no problem. So 1, 2, 3, 4, because I have cis and trans here itself, and then 5.
Oh, so you count the structure separately and then cis and
Exactly,
trans.
exactly. You're asking you how many different isomers are there. So this like I cannot consider them as one. I have to consider them as 2 isomers because I have cis and trans in this itself.
Okay. Sir.
Understood? Right? So 1, 2, 3, 4, 5. Totally fine. Okay. Right. Yeah. So let me ask you this question. So I'm going to give you 4 options. Just a second, people. So I'm adding D here. Okay, both these are CH3s. So the question is, which of the compound can show geometrical isomerism? Which of these 4? Obviously, only one can show geometrical isomerism. Which one is that? This is a little tricky, but if you can just put your mind, you'll be able to answer this question easily. Okay. Now tell me which do you think we can definitely not show? Which option? Just by looking at it, I can say
B, sir.
Yes, definitely right. I have this carbon to have a double bond CH3 CH3 similar group, again CH3 CH3 similar group. So done. One more is also like that. Which one?
C,
C, sir.
Exactly. Again CH3 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 CH3. So these two are gone. So the competition is going to be between either A or D. You think and tell me which will show.
Is it A, sir?
Okay. Now I'll help you in this because it is little. You have to. This is the first time you're seeing this kind of question, and it's very simple. Okay. Now if you look at this, people. So here I have a hydrogen, no issues. So I have a hydrogen CH3 for this carbon atom, no issues. But if I go for this carbon atom, right now what you see is again I have symmetry here. Is it not? So what do you mean by that? That means for this carbon atom, this group and this group are same, is what you have to understand, right? For this carbon atom, I have this and this to be similar, right? So obviously I can say that the two groups are same, meaning that this also cannot show geometrical isomerism. Hope you understood why, right? So this carbon atom, no problem. Hydrogen CH3, no problem. Two different groups. But for this, look at this. 1, 2, 3. Again, 1, 2, 3. So same carbon atom. For if 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 at all I had a CH3 group here, if at all, then yes, it would have shown geometrical isomerism, right? Because that side is different from this side. Okay, so whenever you have ring structures coming, right, go for symmetry, right? If at all the carbon having double bond is involved in the symmetry, then definitely it cannot show geometrical isomerism. Okay, so in this case, A is not the answer. A cannot show geometrical isomerism. Let me look at here, right? So again, I have a H. Again, I have a H and a CH3. So this carbon atom, no problem. But for this carbon atom, right, for this carbon atom, what is happening? Do you see any symmetry? Obviously, this side and this side are different. Same goes with this also. Say I have hydrogen CH3. For this carbon atom, this side and this side are completely different, right? So what is the answer for this question? D is the answer, right? Guys, everybody understood? How is it D?
Yes, sir.
Yes, sir.
Okay, cool. Right, so whenever you have ring structures coming into the picture, please check for symmetry. Okay, if that side and this side are similar, then it cannot show geometrical isomerism. Okay, right? Okay, one last question, then we'll wind up, people. Okay, the question is, please take down. Right. How many different stereoisomers? How many different stereoisomers exist for how many different stereoisomers? Oh. Actually, I forgot to tell you one thing, right? Actually, even in ring structures, even if I don't have a double bond, sometimes like generally what I said, if I have a C double bond C, then only we can talk about geometrical isomerism. But it is not like that. Even in ring structures, I can talk about geometrical isomerism, which I forgot. Let me put it in the next class. Okay. So we'll have some other question now. Please rub that question off because you don't know those stuff. right? So I'm telling you, even in ring structures, I can have cis and trans without even having a double bond. That we'll see tomorrow. Tomorrow's class we'll see. But today we'll take this structure. I mean this question. And guys, please understand all geometry. Okay, what do you mean by diastereomers? You studied in your 12th, right? I mean, in your first chapter, right? What do you mean by diastereomers? We have three things, right? Enantiomers, diastereomers, mesomers, right? So, what do you mean by diastereomers?
That means structures that have geometric isomerism.
Exactly, right? So, the perfect way of defining what the diastereomers is, they are stereoisomers which doesn't
So they're not
have
impossible.
any. Yes.
They're not superimposable on each other.
Yeah. So we should. That's what I'm telling. So they are stereoisomers which doesn't have any mirror image relationship, right? Which doesn't have any. It is not related to the mirrors at all, right? Just the orientations are different. Just the orientations are different in case, just like your geometrical isomers. So please take a note of it. All geometrical isomers are diastereomers. Okay, because they are not related to each other in terms of mirrors or anything else. It's just that the 3D orientations of atoms is different, right? So obviously all geometrical isomers are diastereomers. Okay, and Akshay, I think Akshay or Siddharth, what you told is they are non-superimposable mirror images. That is for enantiomers. Okay, enantiomers are non-superimposable mirror images of each other. Okay, right? Good. So let me ask you this question, and one last question, then you can go enjoy your weekend. Okay. So I have. Why are the markers troubling today? Three. Did I put anything extra? O and CH. This is my E. Right. Next. This is my F. This is my G. Okay. First, take down the structures. I'll give you options. E, F, G structures. You just take down. Okay. Hope you're taking it down. Please take down the options. Option A, E, F, G are resonance structures. E, F, G are resonance structures. Option B, E, comma F and E, comma G. E, comma F and E, comma G are tautomers. Right? The first option was E, F, G are resonance structures. Option B, E, comma F and E, comma G are tautomers. Option C, F and G are geometrical isomers. F and G are geometrical isomers. Option D, F and G are diastereomers. F and G are diastereomers. So let me repeat the options. Option A, E, comma F, comma G are resonance structures. Option B, E, comma F and E, comma G are tautomers. Option C, F and G are geometrical isomers. Option D, F and G are diastereomers. This can be more than one option correct. Okay, tell me which are all the correct statements. I can have
Sir,
more than
C-
one option.
C and D.
Yeah, tell me.
C and D.
C and D. Okay, fine. C and D. C and D, or if I'm telling it is F and G are geometrical isomers, F and G are diastereomers. So F and G are this, right? So F and G are this. You can see OH and CH3 or trans to each other. Here OH and CH3 are cis to each other. Same way, this CH3 and C2H5 are trans to each other, and this CH3 and this one are cis to each other. So definitely F and G are what is the geometrical isomers, and I just now told you all geometrical isomers are diastereomers. So definitely C and D are correct. What about D or A?
Sir, I think A is wrong.
Yeah, A is definitely wrong, right? These are not resonance structures, right? So we know what are resonance structures, right? But anyways, we will see them in depth when I go for resonance. We'll be seeing it in depth. So now please understand that they are not resonance structures. Okay, fine. So definitely the only option which is left out is B. That is, they are telling E and F and E and G are tautomers. Is it not? Now look at this. I have a C double bond O, right? And don't you think I have a hydrogen atom here? Alpha hydrogen is present, right? Now this alpha hydrogen can be removed, so I can have a negative charge put here, put here. Now you can end up with F and G. Obviously, they are diastereomers, or they're geometrical isomers, right? So yes, what are the correct options now? B, C, D. All are correct options. Is it not? So guys, did you understand how they are tautomers? If you don't understand, do what we do. You know what you do, right? We just remove the hydrogen, make a negative charge, draw the resonance structure, and add the H along with oxygen. This is my keto form, and these two are my enol forms. Okay, so the correct option for this question, the correct options for this question would be B, C, and D. A option is wrong. They are not resonance structures. Okay, so we will continue with geometrical isomerism next class, and we'll move on to optical isomerism, right? Then I'll move on to conformational isomerism. I told you, when I have C single bond C, it can undergo rotation, and because of that, I can give some isomerism, right? So all these things tomorrow's class we'll see. Any doubts, people? Everything is
No,
clear?
sir. Yes, sir.
Okay, children, you can go. Thank you.
So,
Bye bye.
Thank you, sir.
Thank you.